In this video, I will be discussing about a technique in integration which we call integration by parts. So, what is integration by parts? Sometimes in calculus, we come across integrals which could be very difficult to evaluate using the techniques we have just learned from the previous videos. For example, integration by u substitution. We use integration by u substitution because we want our integrand to fit to the standard formulas we have in this integral calculus. And also we apply integration by trigonometric substitution when our integrand involves irrational expressions. Now, this is another technique of integration by parts. So, to start with, allow me to derive the formula for integration by parts. By the product rule in differentiation, we know that the derivative of a product, say u and v, where u and v are functions of x, we have u times the derivative of the v function, so this is dv dx plus v times the derivative of u, which is du dx. And if we want to convert this one to its differential form, we have the differential of the product of two functions uv, which is equal to u dv plus v du. And if we subtract both sides of the equation by v du, the v du here at the right hand side of the equation will be cancelled. So we have here the differential of the product of u and v minus v du is equal to u dv. And if we are going to write this equation, wherein the right hand side becomes the left hand side of the equation, we have the left to be at the right. So we have the differential of u times v minus v du. And because this is an equation, we can integrate both sides of the equation. So we have the integral of u dv, which is equal to the integral also of the differential of uv minus the integral of v du, because the integral of a difference is a difference of its individual integrals. Now, we know that the integral of a differential are inverses operations to one another. So this integral and differential cancels each other. So we have uv minus the integral of v du. So now this is the formula that is popularly known as the formula for integration by parts. That the integrand of this integral here is being divided into two parts. The first part is our u, and the second part is the dv part. And the answer is just a product of u and v minus the integral of v du. So when this formula will be used in integrating a particular function, the given integrand must be separated into two parts. The first part is the u part, and the second part is the dv part. Now, the crucial part of this technique is to determine which one is the u part and which one is the dv part. Actually, there is no general rule that can be given as to which of the two factors in our integrand will be the u part and which part will be the dv part. Only by experience and practice that will give us the skill to be able to choose correctly through advanced thinking. Now, when do we use integration by parts? We use integration by parts when we are integrating a logarithmic function, or when we are integrating an inverse trigonometric function or a product of two different functions. So maybe it's a product between algebraic and exponential function, or a product of algebraic and trigonometric functions, or an exponential and a trigonometric function, or a product between algebraic and logarithmic function, or another case is when you are integrating a product of an algebraic and an inverse trigonometric function. So if you have an integrand which is a product of two different functions which fall on these categories, then you may apply integration by parts, which I abbreviated here as IBP. Again, there is no general rule for choosing which part of the integrand is the u part and which part of the integrand is the dv part, but there is a suggestion for choosing a correct u and a correct dv in your integrand. For u, choose something that becomes simpler when differentiated, and for dv, must be a part of the integrand wherein the integral of that part is simple, which means that that dv part is readily integrable. So for example, this example number 1, what is the integral of x cubed times e to the power x squared dx? Now you notice that in this integrand, this is a product of two functions, wherein the first factor is an algebraic function and the second factor is an exponential function. So it falls here on the first category of the product of two different functions. Now, if you want to guess that your u is the function x cubed and your dv is the part which is e to the power x squared dx, no problem with the u, because you can easily differentiate x cubed. But the problem here is that the dv is not readily integrable, because e to the power x squared is an integrand that is not easily integrable. Because what is the integral of e to the power x squared? I know that based from your previous basic knowledge of integration, this is very difficult to integrate. So the choice of your dv might not be a correct dv. So experience and practice would dictate what should be the correct dv here. Now, looking at this dv, e to the power x squared, the derivative of this x squared is not found here, which means that this is not easily integrable, because this is only easily integrable if the derivative of x squared is also found here, and the derivative of x squared involves x, because the derivative of x squared is 2x. So it's good to borrow 1x from x cubed. So rewriting our integrand as the integral of x squared times e to the power x squared x dx, then we can try that our u here is x squared and our dv here is e to the power x squared x dx, because you can try that the differential of u is 2x dx. And solving for your v, I need to integrate both sides of the equation. So we have the integral of dv, and at the right, the integral of e to the power x squared x dx. But you notice that the derivative of x squared is not only x dx, but it is 2x there. So I need to have a 2 in front of my x. So my v is equal to the integral of e to the power x squared 2x dx here. And you might ask a question, where did I get the 2 there? So for this 2, I need to have 1/2 in front of the integral symbol, so that 1/2 times 2 is just equal to 1. Therefore, I can easily integrate now my e to the power x squared 2x dx, because the derivative of x squared is already here. So our v is equal to 1/2 of e to the power x squared. And now that I have my u here, and I have also my v here, my du and my dv here, then I can substitute this one to my integrand here. So we have our integrand as u, because instead of writing x squared, I will write the u representation there. And instead of writing this part here, this is my dv representation. So my integrand is being transformed to u dv form, wherein the u is my x squared and my dv is the e to the power x squared x dx. And according to the formula here, that the integral of u dv is uv minus the integral of v du. So applying the formula, we have uv minus the integral of v du. And we know already what is our u. Our u is x squared, and our v is 1/2 e to the power x squared. And this will be subtracted by the integral of v, which is 1/2 of e to the power x squared times the du, which is 2x dx. So multiplying this 1/2, we have 1/2 of x squared times e to the power x squared. And this will be subtracted by 1/2 of the integral of e to the power x squared 2x dx here. And you notice that this 2x is the derivative of x squared. So therefore, we can integrate this integrand here. So we have 1/2 of x squared times e to the power x squared minus 1/2 of e to the power x squared plus the constant of integration c. So this is now our answer for this example when we apply integration by parts. Now let's proceed to our example number 2. What is the integral of x squared times e to the power x dx? Now, looking at this integrand, we notice that it's a product between an algebraic and again an exponential function. So we may guess that our u here is equal to x squared, and our dv is equal to e to the power x dx. And how do we know that this is the correct u and the correct dv? We just get the differential of our u, and the differential of our u, which is x squared, is 2x dx. And to get for our v here, because this is already our dv, our goal is to solve for our v, we need to integrate both sides of the equation. So this is the integral of dv and the integral of e to the power x dx. And we know that integration and differentiation are inverse operations. So this will cancel each other. So what remains is just the v. And the v is just e to the power x, because the derivative of x is just 1 or 1 dx for its differential. So substituting our u part and our dv part here to our integrand, we have the integral of u dv here, wherein our u is this x squared and our dv part is the e to the power x dx. And according to the formula, the integral of u dv is uv minus the integral of v du. So we just substitute our u and our v here. So u, which is equal to x squared, times our v, which is e to the power x. And this will be subtracted by the integral of v, which is e to the power x, times our du, which is 2x dx. And factoring our constant outside the integral symbol, we have x squared times e to the power x minus 2 times the integral of e to the power x dx here. And you notice that the derivative of x is not x. So there is an extra integrand here, which is the x. So therefore, we cannot easily integrate this one using integration by substitution. So what will you do is to apply again another integration by parts. Actually, we can repeatedly apply integration by parts in solving for the integral of the given function. So rewriting this one, we have x squared times e to the power x minus 2 times the integral of x times e to the power x dx, wherein this x is our new u. So our new u this time is equal to x, and our new dv is the e to the power x dx, because the remaining part is our dv here. So solving for our differential of u, we have dx, and solving for our v, we need to integrate both sides of the equation. So we have the integral of e to the power x dx. And we know that integration and differentiation are inverse operations to one another. Then these two cancels, so what remains is v. So v is equal to the integral of e to the power x dx, and we know that the integral is e to the power x. Now that we have our u here, which is x, and our dv, which is this one here, then we can substitute this one to this integrand. So we have x squared e to the power x minus 2 times the integral of u dv, because our u is this x, and instead of writing e to the power x dx, we write dv. And according to the formula, that the integral of u dv is just uv minus the integral of v du. Now take note that we need to place the whole thing inside a bracket to indicate that the whole thing will be multiplied by -2. So make it a habit that in mathematics we need to use brackets, parentheses, and braces in order to keep things in order. So if you are not using most of the time the brackets, the braces, and the parentheses, then it is a bad habit. So make it a habit this time. So looking at this formula, you need the u and the v here, which is this one. And also you need the v and the du, which is this one here. So substituting that one to the formula, we have x squared times e to the power x minus 2 times the u, which is x, and the v, which is e to the power x, minus the integral of the v, which is e to the power x, and the du, which is dx here. So simplifying our answer, we have x squared e to the power x minus 2x e to the power x, and we know that minus 2 times minus becomes positive 2 times the integral of e to the power x dx. And looking at this integrand, we know that this is very easy to integrate. So we have x squared times e to the power x minus 2x times e to the power x plus 2 times e to the power x, because the integral of e to the power x dx is e to the x. And you can check that the differential of e to the power x is e to the power x dx. And this will be added to the constant of integration c. So this is now our answer for this example number 2. Now, as you can see that this example number 2 differs from the first example, because here in example 2, we applied integration by parts twice here, while in the example number 1, we applied only integration by parts only one time. Now let's proceed to our third example here. What is the integral of x squared times sine 2x dx? So here we can try that our u is maybe x squared and our dv maybe is sine 2x dx here, because we might guess that this is our u and is sine 2x dx is our dv. And how do you know that this is a correct u and correct dv? We need to find the differential of our u, and the differential of our u is 2x dx. And to find the v in this dv, we need to integrate dv at the left side of the equation and also integrate the right hand side, which is the sine 2x dx. And we know that this is our v. So v is equal to the integral of sine 2x dx. Now remember that if this is our argument of sine, then by the chain rule, the derivative must be there also. And we know that the derivative of 2x is 2, but we don't have a 2 there. So we might as well add a 2 as a factor. So we have 2 dx here. And you might ask a question, where did I get this 2? I get a 2 by multiplying 2 over 2. So I have here 1/2, because 1/2 times 2 is just 2 over 2. And I do this so that I can integrate this sine 2x here. So we have 1/2 of the negative of cosine 2x, because we know that the integral of sine is the negative cosine. So our v here is just negative 1/2 of cosine 2x. Now that we have our u and we have also our v, because we can integrate this dv here and also our du here from our u, then we can substitute that one to our integrand. So this is equal to the integral of u dv, because this x squared is our u and this sine 2x dx is our dv here. And according to the formula for integration by parts, we have the integral of u dv is uv minus the integral of v du here. So substituting back our original variable, our u is x squared and our v is negative 1/2 of cosine 2x, and this will be subtracted by the integral of our v, which is 1/2 of the negative of cosine 2x times our du, which is 2x dx here. So factoring these constants here outside the integral symbol and also this constant in front of x squared, we have negative 1/2 x squared times cosine 2x. And this will be added to 1/2 times 2. And this is multiplied to the integral of cosine 2x times x dx, because the 2 here is already written in front of the integral symbol. Now, as you can see that the derivative of 2x is not x, but it is just 2. So we have an extra x here. So we cannot easily integrate this one. Now, to integrate it further, we apply again another integration by parts by rewriting this answer as 1/2 of x squared times cosine 2x plus 2 over 2, which is 1, times the integral of x cosine 2x dx by writing this x in front of cosine 2x. So here, we need to apply again another integration by parts for this integral here. So we might guess that this is our u and this is our dv here. So let u be x and our dv is cosine 2x dx. And you can check whether this is correct by finding the differential of x, which is dx, and finding the v in this dv here by integrating both sides of the equation. So this is the integral of cosine 2x dx. And we know that by chain rule, the derivative of 2x is 2. But we don't have a 2 here. So we need to provide a 2 for that integrand. So this is the integral of cosine 2x 2 dx. And to have a balance for this 2, we need to write 1/2 in front of the integral symbol. So that 1/2 times 2 is just 1. And we know that the integral of cosine is positive sign. So this is 1/2 times the sine of 2x here. So substituting this one to our integral here, we have negative 1/2 x squared times cosine 2x plus the integral of u dv, because instead of writing x, you will write u, because that is our representation here. And instead of writing cosine 2x dx, we will write dv here. And according to the formula that the integral of u dv is just u times v minus the integral of v du. So this 1 is the integral of u dv according to the formula of the integration by parts. So we have negative 1/2 x squared times cosine 2x plus the product of our u, which is x, times the v, which is 1/2 of sine 2x minus the integral of our v, which is 1/2 of sine 2x times du, which is dx. And factoring this 1/2 outside the integral symbol, we have negative 1/2 x squared cosine 2x plus 1/2 x times sine 2x minus 1/2 times the integral of sine 2x dx. But we know that by the chain rule, the derivative of 2x is 2. But we don't have a 2 here. So we need to provide a 2 for this one. And to have a balance, I need to multiply by 1/2 outside the integral symbol. So we have negative 1/2 x squared times cosine 2x plus 1/2 of x times sine 2x minus 1/4 of the integral of sine 2x to dx, which is negative cosine 2x. And negative times negative becomes positive here. And this will be added to the constant of integration c. So this is now our answer for this example number 3. Now let's proceed to our example number 4. What is the integral of e to the power 2x times cosine 3x dx? Now looking at this integrand, this is a product of an exponential function and a trigonometric function. So we might guess that our u here is our e to the power 2x, and our dv part here is the remaining expression, which is the cosine 3x dx. And how do we know that these are the correct u and dv? If we can easily differentiate our u. And we know that the differential of e to the power 2x is e to the power 2x times 2 dx, because the derivative of 2x is 2 by the chain rule. So we have our du, which is equal to 2 e to the power 2x dx here. And for our v from this dv, I need to integrate both sides of the equation. So we have the integral of cosine 3x 3 dx, because I need to provide a 3 here since the derivative of 3x is 3. But I need to have a balance by multiplying 1/3 in front of the integral symbol. So we have our b, which is equal to 1/3 of sine 3x, because we know that the integral of cosine is positive sine. So going back to our integrand here, instead of writing e to the 2x, we will write u, because that is our representation here. And instead of writing cosine 3x dx, you will write dv here, because this is our representation for dv. So this is now the integral of u dv. And applying the formula for integration by parts, we have uv minus the integral of v du. So substituting back our expressions for u, which is e to the 2x times our v, which is this one here, times 1/3 of sine 3x minus the integral of our v, which is 1/3 of sine 3x, and this is multiplied by du, which is 2 e to the power 2x dx. So factoring outside these constants in front of the integral symbol, and also this 1/3 in front of e to the 2x, we have 1/3 of e to the power 2x times sine 3x minus 2/3 times the integral of e to the power 2x sine 3x dx here. And you notice that our integrand is almost the same to our original integrand, but the only difference is that this is only sine 3x, but here it is cosine 3x. So again, because this is a product of an exponential and a trigonometric function, we might apply as well integration by parts for the second time. So here we will represent u as e to the 2x, and the remaining part is our dv here. So dv is equal to sine 3x dx. So solving for our du here, this is e to the power 2x 2 dx, because the derivative of 2x is 2 by the chain rule. And for our v from this dv, I need to integrate both sides of the equation. So we have the integral of sine 3x dx. And our v here is equal to the integral of sine 3x 3 dx, because I need to provide 3 for the derivative of 3x, but I need to have a balance of 1/3 in front of the integral symbol. So our v here is equal to 1/3 times the negative of cosine 3x, because we know that the integral of sine is negative cosine. So our v is negative 1/3 cosine 3x, and our u is e to the power 2x, but our du is e to the 2x 2 dx, and our dv here is sine 3x dx. So instead of writing e to the 2x, we write as u, and instead of writing sine 3x dx, we will write dv. And of course, you still have this part of your answer, which is 1/3 of e to the 2x sine 3x. So applying the formula for integration by parts, we have e to the 2x sine 3x minus 2/3 of the integral of u dv, which is uv minus the integral of v du here. And you notice that if you substitute back our original variables, original functions, we have minus 2/3 times our u, which is e to the power 2x here, and our v, which is the negative 1/3 cosine 3x, and this will be added to 2/3 of our integral of v, which is this one, the negative 1/3 of cosine 3x times the du, which is e to the power 2x 2 dx here. So simplifying our answer here, we have 1/3 of e to the power 2x sine 3x plus 2/9, because negative 2/3 and negative 1/3 is positive 2/9. And this is multiplied by e to the power 2x times cosine 3x. And this will be added to 2/3 times negative 1/3 because of this, times 2 because of this 2 here. And this is multiplied by the integral of e to the power 2x times cosine 3x dx. So simplifying our answer here, which is 1/3 of e to the power 2x sine 3x added to 2 over 9 of e to the power 2x cosine 3x minus 4 over 9 of the integral of e to the power 2x cosine 3x dx. And we notice that this integrand is the same as our integrand here. So it's like we go back to the original given, which is the integral of e to the power 2x cosine 3x dx here. So what will you do is to move this one to the left side of the equation so that this one will combine here. So this becomes 4 over 9, so it becomes positive plus 1 because this given here is understood to have a coefficient of 1. So 4 over 9 plus 1 times the integral of e to the power 2x cosine 3x dx. And this is equal to 1/3 of e to the power 2x sine 3x plus 2 over 9 of e to the power 2x cosine 3x. And this is already 0 here because you are adding both sides of the equation by this quantity. So this quantity will be cancelled at the right because it combines here at the left side of the equation. And we know that this 4 over 9 plus 1 is just 13 over 9. So how will you eliminate this 13 over 9? Because the given is only this one. What will you do is to multiply both sides of the equation by 9 over 13. So multiplying 9 over 13 here, we have 9 over 13 times 4 over 9 plus 1 times the integral of e to the power 2x times cosine 3x dx. And this is equal to 9 over 13 times 1/3 here times e to the power 2x times sine 3x plus 9 over 13 times 2 over 9 times e to the power 2x cosine 3x. And this will be added to the constant of integration c. So we have a c here in this line. So you can see that we are multiplying each term in this equation by 9 over 13. Why? So as to eliminate this 4 over 9 plus 1, because this 4 over 9 plus 1, which is 13 over 9, when multiplied by 9 over 13 will be equal to 1. So we have 1 times the integral of e to the power 2x cosine 3x dx, which is equal to 3 over 13, because the 3 in this 9 and the 3 in this denominator cancels each other. So we have 3 over 13 times e to the power 2x sine 3x plus 2 over 13, because the 9 here and this 9 in the denominator cancels each other. So we have 2 over 13 times e to the 2x times cosine 3x plus the constant of integration c. And this is our answer for this example number 4. And this example is slightly different from example 3 because although we applied integration by parts twice, the same as example number 3, but we come up an integrand here which is the same from the given integrand. So the only difference is that we just combine this integrand with the given so that we can come up with this answer. Now let's proceed to our example number 5, wherein our integrand is a product of an algebraic and a logarithmic function. So what is the integral of x squared times the square of ln x dx? Now here, we might guess that our u is x squared and our dv here is our ln x quantity squared dx. And you can see that we can easily differentiate x squared. However, solving for v by integrating both sides of the equation is a problem here because we don't know how to integrate this ln x quantity squared. We know how to differentiate this one, but we don't know as of this time how to integrate a logarithmic function. So this is a signal that we might choose a wrong u and a wrong dv here. So what will you do is to switch these two functions. So rewriting our integrand as the ln squared x times x squared dx here, so that our u is now the square of ln x and our dv here is our x squared dx, because we can easily integrate this x squared dx. So solving for differential of u, we have 2 times the ln x times dx over x by the power rule. Because our exponent is 2, so by the power rule we have 2 here times ln x to the power of 1 times the derivative of the base, which is ln x, which is dx over x, or 1 over x dx. So this is now our differential of the square of ln x. And for our v, which will be obtained from this equation, we need to integrate both sides of the equation here. So we have integral of x squared dx. So our v is x cubed over 3, which can be easily obtained when our dv is x squared dx. So how do we know that we choose the correct dv? If you can readily integrate that dv. So instead of writing ln x squared, you will write u. So this is our u here. And instead of writing x squared dx, that is our dv here. So instead of writing that one, I will write dv. So this is now the integral of u dv. And using the formula for the integration by parts, we have u times v minus the integral of v du. So substituting back our representation for u, which is the square of ln x times the v, which is x cubed over 3 minus the integral of v du, and our v is x cubed over 3 times du, which is 2 times the ln x times dx over x. So moving all the constants here in front of each term, we have 1/3 of x cubed times the square of ln x minus 1/3 times 2 here times the integral of x squared times ln x dx, because one of the x in this x cube and the x in the denominator here will be cancelled. So what remains is x squared ln x dx. So we have 1/3 of x cubed times the square of ln x minus 2/3 times the integral of ln x times x squared dx. If we will switch the position of x squared and this ln x, because we need to pick again another u and dv here. when we apply for the second time our integration by parts technique. And this is because we cannot easily integrate this one because this is a product of still an algebraic function and a logarithmic function. So we need to apply for the second time another integration by parts. So our u this time is ln x, which is 1 less in the exponent of our first u. And our dv here is equal to x squared dx, which is the same with our dv here. So solving for our du, we have 1 over x dx because the derivative of ln x is 1 over x. And for our v, we need to integrate both sides of the equation. So we have integral of x squared dx. And we know that the integral of x squared is x cubed over 3. So instead of writing ln x, we have u, and instead of writing x squared dx, we will write dv here. And of course, there is still a part of its answer, a part of the solution, which is this one here. So applying the formula for the integration by parts, we have 1/3 times x cubed times the square of ln x minus 2/3 of our integral of u dv, which is, according to the formula, is uv minus the integral of v du here. So substituting our original functions there, we have 1/3 of x cubed times the square of ln x minus the 2/3 of the product of u, which is ln x times the v, which is x cubed over 3 here. And this will be subtracted by the integral of v, which is x cubed over 3 times du, which is 1 over x dx. And of course, the whole thing will be multiplied by negative 2/3. So we have 1/3 of x cubed times the square of ln x minus 2 over 9 because of this 3 here times x cubed ln x plus 2 over 9 of the integral of x squared dx, because we have a 1/3 here times the 2/3 here. But because this is negative and this is negative, we have a positive here. So writing our final answer, we have 1/3 times x cubed times the square of ln x minus 2 over 9 times x cubed times ln x plus 2 over 27, because the integral of x squared is x cubed over 3. So the denominator of 3 when multiplied to 2 over 9 becomes 2 over 27. And this will be multiplied by x cubed, which is the integral of that. And this will be added to the constant of integration, c. So this is our answer for this example number 5. Now let's proceed to our last example here. What is the integral of arctangent of 3x dx? Now as you can see that our integrand is just only one function, but it is an inverse trigonometric function. This inverse trigonometric function, we can still apply our integration by parts when we let our u be equal to arctangent of 3x. And you can recall that the derivative of arctangent is just the square of 1 and the square of 3x here. And where did I get the 1? The 1 is the coefficient of arctangent here. And of course, we need to find the derivative of 3x, which is 3 dx. So our differential of u is 3 dx over 1 plus 9x squared. And you can recall this one from your differential calculus. And also for our dv is only dx here. So therefore, the integral of dv is just the integral of dx. And we know that the integral of the differential cancels each other. So our v is equal to x. So instead of writing arctangent of 3x, you will write its representation, which is u. And instead of writing dx here, I will write its representation, which is dv here. So our integral becomes the integral of u dv. And according to the formula for integration by parts, this is equal to uv minus the integral of v du. So substituting back our original representations, this u, which is the arctangent of 3x, will be multiplied to our v, which is x. And this will be subtracted by the integral of v, which is x, and the differential of u, which is 3 dx over 1 plus 9x squared there. So rewriting our answer, we have x when you write x in front of arctangent. So we have x times the arctangent of 3x minus 3 times the integral of x dx over 1 plus 9x squared, because we just factor out 3 in front of the integral symbol. And looking at this integrand, there's no need to apply another integration by parts, because we can solve this integrand using integration by u substitution, or in other words, integration by substitution. Because if we let our denominator as w, so 1 plus 9x squared is our w. I'm not using u this time because I have my u here. We notice that our dw is just 18x dx, because the derivative of 1 is 0 and the derivative of 9x squared is 18x. But we don't have the 18 in our integrand here. We have only x dx. So we need to eliminate the 18 by dividing both sides of the equation by 18. So we have dw over 18 is equal to x dx. So by substitution, we have x times the arctangent of 3x minus 3 times the integral of our x dx, which is dw over 18, and this will be divided by this 1 minus 9x squared, which is our w. So this is over w. And factoring this 18 in the denominator of dw outside the integral symbol, we have x times the arctangent of 3x minus 3 over 18 times the integral of dw over w. And we have x times the arctangent of 3x minus 1/6 of the natural log of w, because we know that the integral of dw over w is the natural log of w. And of course, this will be added to the constant of integration, c. So going back to our original representation for w, which is this one, we have x times the arctangent of 3x minus 1/6 of the natural log of 1 plus 9x squared plus the constant of integration c. And this is our answer for this example number 6. And you notice that we can still apply integration by parts even if this is only one function, which is the inverse trigonometric function. And that's it. If you learned something today, please check out my channel for more videos like this and click subscribe. Click the notification bell below so you'll get notified whenever I'll be posting a new video. Don't forget to like this video to show your support. And always remember to math your way up. Thank you.